Go to the next slide. Okay, so just a little background and like the motivation for our project. Circadian rhythm controls the body's sleep-wake cycle via hormones. It also controls things like the feeding patterns. And if the circadian rhythm is not properly aligned with the light-dark pattern or the person's actual sleeping pattern, then you can have sleep disorders come up like insomnia or excessive daytime sleepiness or other health problems like weight gain, lack of alertness. And the reason why we're measuring core body temperature is that core body temperature and circadian rhythm are intimately linked. So you can see in these two graphs at the bottom, on the left shows the core body temperature throughout the day with sleep. So the shaded area is sleep. And then the right shows throughout the day without sleep. So even without sleep, the core body temperature changes with the circadian rhythm. So it's a good way to track it. So current solutions right now for measuring core body temperature are rectal thermometer, which is kind of the gold standard for core body temperature. It's the most accurate. The only problem is that it's invasive, so it's not clinically acceptable. It also requires that each measurement be taken manually. And when you're doing something like trying to track circadian rhythm, where you have to make a bunch of measurements over a long period of time, it's not really feasible. The other solution is the IR temporal artery thermometer. So the good thing about this is that it's not invasive, but it's not as accurate as the rectal thermometer, and it also requires that each measurement be taken manually. So our customer, Dr. Woodson, is an otolaryngologist who focuses his research on sleep medicine. So after meeting with him, we came up with some of the top customer needs and the target specs that go with them. So the first is that it records for 2 weeks without dying. So it just needs to record for 2 weeks. That's the marginal and ideal value. And then it needs to sample at an acceptable frequency. And this is just so we can get the real circadian rhythm curve. So we said 20 samples per hour, or at best 60 samples per hour. And then it needs to measure the body temperature with an acceptable accuracy compared to previously validated thermometers. So from that, our project objective statement is just to design and build a prototype for a non-invasive device that can accurately measure and transmit core body temperature to study circadian rhythm by May 1st, 2020 for under $1,500.
Okay, so for our project decomposition and action plan, this just allowed us to further develop our customer needs and develop a plan for how we're going to tackle these customer needs and target specifications. So as Mike stated 2 slides ago, those are some of our top customer needs listed there. And then all our customer needs basically stem from 3 main branches. And this includes that our device needs to be able to provide sufficient data for research purposes. It needs to be safe for the patient, and it needs to provide an accurate alternative to current solutions. This meaning that it needs to be non-invasive, because as we saw at current solutions and the gold standard is very invasive. One of the customer needs that I want to address that's listed here, it says measures pulse. However, this was actually omitted from our final design, as this was provided to us as a secondary customer need by our sponsor. And so we wanted to focus on the main primary customer need, which was measuring core body temperature accurately. And then here we can just see one of those decomposition diagrams that I was talking about. So this was done for each customer need and allowed us to further think about design choices that we could take. So for this one particularly, we can see that it's for accurate temperature and pulse measurement. And obviously pulse measurement was omitted, but for accurate temperature, we came up with 2 different design choices we could take. We could either use an infrared temperature sensor, or we can use a contact thermopile sensor to answer this customer need. And so by doing this for every customer need, we could ensure that our device was able to meet each customer need.
So for the final design concept overview, in the ideal scenario where we had access to testing facilities, we would have came up with a fully functional prototype that was wearable. This prototype would have had 2 main components. First, the non-invasive earpiece sensor. This would have included an infrared thermopile that Raj was just talking about, embedded in the sensor, and then a clip around the ear to ensure that the device was stable and recording tympanic membrane temperature. Secondly, we would have an Arduino and circuitry component, which is used for signal conditioning and storing the data, and these would be connected with a wire. However, due to the ongoing challenges of the COVID-19 pandemic, The final design had to be broken into 3 phases. First, the mechanical phase. This consists of 2 3D printed casings for the Arduino and the ear sensor respectively. Secondly, the electrical phase. This consisted of preliminary circuit schematic and a built prototype on a breadboard. And third, the computing portion of the design. This consisted of the code that was intended to be used in the Arduino, which functions included sampling, filtering, and storing the signal.
Okay, so for the mechanical portion of our design, as Tom stated, it's mostly the housing and the earpiece housing. So we wanted to make sure that our device was durable, and the materials we chose were also durable and comfortable, and also semi-biocompatible, as the earpiece was actually going to ultimately end up in the ear. So for the housing, this was done for the Arduino and PCP board housing, and this housing ultimately allows us to allow the patient to wear the device and transport it from one place to another during daily activities. The way it does is it's just like any other casing for an Arduino, except ours just has a 3-prong buckle system where it just goes on the patient's hip area and they're able to carry it through daily activities, and the wire would just run up and then into the ear. And so the front side just has some air vents to make sure that we're not overheating any of our components, and so that allows for better transportation as well. And then the earpiece can be seen right here. This was also 3D printed using that ABA polymer. However, if this was done properly, we would have had this around the ear part be a little bit more of like a silicone rubber to allow for variability in ear sizes. And then this part where it would actually go inside the ear would also be silicone to allow for better insulation and comfortability for the patient.
All right, so moving on to the physical design of the electrical portion, as Raj was saying, the casing was to case the Arduino and any other components that came with it. So as looking at the right image, that is the PCB board with the breadboard on top of it. You can't see underneath it, but I can show it right here. There are pins on the bottom of the design. This would go on top of these pins match up directly to an Arduino. So you could just stick it on top and the Arduino will be connected to the PCB board, in which from here, these wires, these white wires, go into the design of the constant current source that's connected to it. So inside the casing, we can have the entirety of the Arduino, which is the power source, and the thing measuring our design with the voltmeter, as well as the sensor coming out of it. So in the process of the electrical design, there are 3 main components: the constant current source, the voltmeter, and the sensor, with the main focus being on the constant current source, as it maintains the integrity of the design and the power flowing through the circuit. So if we look at the top sketch, it displays an A, a V, and the sensor. The A stands for current, as that's the constant current source. That's what's allowing the current load to flow through to the sensor. And this displays a 4-wire measurement system, which is the standard for R2D sensor measurements. The sensor, whenever there's a temperature change, it changes the resistance of the sensor. And in order to get an accurate measurement, we are using a voltmeter instead of an ohm meter. And the reason for that is that the ohm meter draws too much current towards itself. So you're not getting the accurate constant current flowing through the sensor. So with the voltmeter's wire system has extremely high impedance. And with the extremely high impedance, it effectively means that no current will flow through the voltmeter. Thus, there will always be accurate measurement of voltage across the sensor that we can calibrate in accordance or proportional to the resistance that's being changed with the sensor. This also means that we can actually tell what the temperature is at those given voltages. And we created this schematic. This schematic illustrates the constant current source that we used in our design. Our design uses a constant current source chip, which is more effective. but we show that there's a signal, which is the little squiggle, says 5 volts peak to peak, 60 hertz, 0 degrees. That effectively creates the signal. It's pumping through voltage. We also have a Zener dial, which is the black arrow. This creates a constant voltage drop before it goes over the components that are variable. So there's no change in the constant voltage that's coming in. And then we have the Arduino that's connected to it for the power source.
So this is the Arduino code, and the main goal of the code is to take the signal that's coming from the circuit that Robert just described, filter it, and then store it at the regular intervals of the sampling rate that we have into the SD card. So the way an Arduino works is you have void setup, which every time the device is turned on, that is run first, and then it'll go into void loop until the device is turned off. So setup will initialize the SD card, and what we have it doing is that it will create a new file every time the device is turned on. And the goal of this is to make it so nothing is overwritten just because you accidentally switched off and on the device. It'll look for a new file that it hasn't been created yet and then create it. And then in the loop, it waits 3 minutes or whatever the sampling rate is, and that 3 minutes is defined as a integer or just a constant above. It opens the file, writes to the file the time, and then gets the temperature value from the sensor, and then undergoes what that big chunk right there between like long data sample and those W's is digital filtering, which I'll explain in the next slide. But then it closes, writes to the file, closes it, and then to the right you can see it's because of the work that Robert did with this circuitry, we really only have to just read from the sensor. The idea behind the opening and closing of the file every iteration of the loop is for data corruption. If the device turns off when the file is not closed, there's a higher risk of the data just being corrupted. So this theoretically prevents a lot of data corruption from happening. This is to define digital filtering, which is just making filtering happen, but in code. The way it's done is by using a difference equation, which is shown to the right there, which is just the difference of inputs and outputs to the difference equation over time, using specified coefficients, which are to the left, which are identified as those A and B values. And then the implementation to the bottom left is how that is actually done. These coefficients we got at least from MATLAB. You can use the MATLAB filter function with specified order of the filter as well as the frequency range, and it'll spit out at you those coefficients. There's also a way of hand calculating it, but MATLAB offers that useful function. This right here is for a fifth order bandpass filter from 10 to 12 hertz. It's probably not what we're going to use. It's just what I had to show as an example. Because we couldn't put it all together and test it, we weren't sure what exactly the frequency range of the noise that the device would be providing given all the different possible sources of noise in it. So we knew that this would need to be included to filter out the noise that was there, but we weren't quite sure what the noise was going to look like. So this is how the digital filtering looks as is.
Moving on to the validation of the circuitry. So as seen before, we were using an Arduino microcontroller to provide the voltage source to the circuitry. And then we also implemented certain components in conjunction with a BJT transistor that was NPN orientation. And the reasoning for this is a very common setup inside of constant current source chips, and we use a constant current source chip in our design. We also added the Zener diode, which is also very common amongst constant current sources. This just controls the voltage drop going from any type of signal from the voltage source. So you won't have any variability of that before it gets converted into a constant current. And then we use multimeter and current probes to make sure that at the final stage of where the sensor would be in place, that the current remains constant, even if we changed the signal from 250 millivolts to 5 volts in increments of 250 millivolts. And then we variable the resistors that were in play there from 1 kilo ohm to 10 kilo ohm. and in each orientation, we had constant current flowing to the sensor.
So another example of validation testing that we would have done is the biocompatibility test. This sensor is going to be contacting the ear for a long period of time, 2 weeks, as we mentioned. So it's important to verify the safety of the material that we're using. And even though that we know the material to be biocompatible, we still thought verifying that would be important. So first we would initially, for a short duration, put the device on the forearm and just see any short-term skin reactions to it. Assuming there aren't any, we would next put the device in the environment that it's going to be in this case the ear, for the period of a day. And we're assuming that if no redness or irritation occurred over the period of a day, the subject will likely be okay. And then repeating this test for a few more subjects just to get a broader array of subjects tested.
This is the testing and validation for the SD card storage, which is just to quickly show that the 8 GB SD card that we chose will be way more than sufficient. The device stores 2 4-byte integer values, time and temperature, every iteration, which we currently have set to 20 an hour. So 20 per hour times 24 hours and 14 days, it's going to be 58 kilobytes for the 8 GB we have stored, which we have more than enough storage.
Okay, so then looking at all of our testing and validation and our 3-phase design, we wanted to make sure that this design still met functional requirements and it was able to meet these performance claims that we initially had made towards the end of last semester. So this table just quickly compares our target specifications that we had to our tested value. As you can see, 1 and 3 actually don't have an applicable tested value. However, theoretically, we would assume that these would pass based on our working code and circuit design along with proper testing procedures. And so this was also done for the customer needs. And our customer needs were split up into 2 sections, functionality customer needs and safety customer needs. And this is, again, just a segment of that table. The way we were able to verify our device meets these customer needs is by looking at what testing and validation relates to what customer need. And by doing procedures that verify the customer need, we can ensure that our device is able to meet performance claims.
So just to quickly look at the risk analysis with our device, obviously any device is going to have potential risks associated with it. So we considered these risks, tabulated them, and included a few on the right of the slide there. We classified each risk according to the phase of the design that it would affect, so mechanical, electrical, or computing. Probability of each risk was assigned pretty generously, I think, because without a functional prototype, we're not sure of some things like exactly how much signal noise there's going to be. Also, the severity factor you can see there is assigned from the viewpoint of someone using the device, which is why, as you can see, the heat generation severity is an 8, which is much higher than the noise severity of a 3, just because it poses a more imminent threat to the user. And then finally, the risk mitigation plans are on the right. Many of these were addressed in specific design choices we made, such as the ventilation slots on the Arduino casing that Raj mentioned earlier.
All right, so at the end of this semester, we were able to create this device by using a few components. Those would be the Arduino Uno, which costs about $16, an SD card that costs us around $6, the constant current source chip that we use to control the current going in and out of the sensor was $15. The 3D printed case estimated around $5, and then the sensor uses the ZTP135IR thermopile sensor, which ran about $2 at $1.96. All in all, the total cost of the device at this stage was $44.22.
So Project Legacy, as we've stated several times, we were not able to actually put the device all together due to the COVID crisis going on right now. So we got as far as being able to completely assemble, or as far as we can assemble, the 3 different kind of components we left it up in. So then Legacy would be to actually put it together and go through the testing procedures that we've laid out and any other that would be thought of, because we can't really recommend anything if we don't, because we didn't get to that point where we could see what worked and what really didn't work.
And finally, we'll just talk about some recommended design changes that we would make. First of all, for the completion of the prototype that we have right now, obviously we would need to combine the mechanical, electrical, and computing phases. The first step for that would be converting the circuit from the breadboard construction to the printed circuit board after proper testing for potential redesign of the circuit. Secondly, we would refine the filtering code because, as we've mentioned, we don't know exactly what this signal coming from the sensor and circuitry is going to look like. So we would have to adjust the cutoff frequencies and coefficients in the filtering code. Outside of the, can you go back? Outside of the design we have, some other redesign possibilities that we considered was wireless transmission of the signal. This would significantly reduce the noise, most likely, because there's no more movement of a wire if we were to do it this way. However, this was challenging for us to address as a group. Secondly, the data storage method. The SD card is most likely not the most practical form of storing data nowadays. We would look at USB or wireless potential there. And finally, the re-addition of the pulse sensor. This would give Dr. Woodson another valuable indicator for the circadian rhythm. I believe that's it. So we'll take any questions.
Great, thanks. Any questions?
Well, this is Guy Garcia here. Hey guys, you had these pictures or figures showing a case and a circuit. I just want to double check. I mean, are these things you actually printed the case and built that circuit, or are those only theoretical?
So I guess I'll start. So the circuit design that we have for this theoretically would work. If you plug in the Arduino, the only issue is whether or not it'll be proper, the current will flow properly. There's one thing that we lacked in the design, which was having a proper workstation with proper voltage meters and current sources. The reason for that is that those sources automatically tell you if there is a short in the circuit, whereas if I plugged in the Arduino directly to this, which is just a click away, then it wouldn't tell us if the design has a short in it or not, which could ultimately damage the entire device. So before we would attach it to the Arduino microcontroller, we would first use the voltage sources to test to make sure there's no short circuit in the design. And whatever, like at the end of our presentation, we mentioned like making sure that there's a proper schematic design for this physically. But overall, it's connected exactly the way you would appropriately connect it to a regular.
Let me just interrupt you here for a second. My question was, you have this photograph of an actual circuit board. So I was just wondering, is this a prototype you guys built, or is just like a figure to illustrate what it would look like?
Oh no, this is the exact build that we have in the photo. So this is the sensor that we have, the thermopile sensor that would be going inside of the ear. And this is connected to the constant current source chip, which is this blue chip that's on top of the breadboard. This breadboard is attached to the PCB board that's right here. And then these prongs, these pins right here, not sure if you can see that. Let me know if you can see that or not.
Yeah,
Do you want to stop sharing and then just that way you'll show a full screen and we can see the prototype better?
Yeah, let me do that. Okay, there you guys.
That's better. Yeah. Okay, there you go.
Okay.
So these pins right here, they would connect. So this is an actual design that we created. So this is a real physical prototype. We didn't theoretically make it. You can test this.
Okay, oh, awesome.
Good.
Yeah, go ahead, Dr. Woodson.
I have kind of simple non-engineering question, or actually, I don't know if they're simple or not. They're basic to me. What was the biggest challenge from an engineering point of view that you ran against? So that's kind of a global question. And then secondly, just to educate me, when you look at like things like an infrared sensor, obviously you could have a sensor that, let's say, went from 0 degrees Kelvin to 1,000,000 degrees Kelvin or something, right? Or you could have infrared sensors that probably have a limited range. I would assume that they have different sort of power or voltage characteristics. How do you decide which ones to use, and what challenges did you have in that regard?
The challenge in that was that a lot of the components that we have, when we originally made the design, we weren't using a constant current source. We first had to test a little bit before we knew that the constant current source is what you needed across a sensor like this, especially one that's going inside the ear, because in electronics, the most important part is the current and not the voltage. So when you have a variable or you have a constant voltage source, if your resistance is changing, then similarly the current will also be adjusting, and that's more dangerous than a voltage. So that's something that we first needed to test, because at first when we were having just a constant voltage source, it wasn't reading what we wanted to read properly, because we're also using an ohm meter. But once we did more research into it, we realized that we need a constant current source and we need to be measuring voltage. And that's how we were going to calibrate it. Another issue, I guess, would have been that before we were incorporating a chip, a constant current source chip, that would essentially be doing all the work for us circuit-wise. For that portion, we were designing the constant current source with regular components, and the difficulty with that was once you have created a constant current source, the voltage drop across each component can be different. And that's why the struggle when we were making the simulation for it in the first schematic with the digital microcontroller and the Zener diode, all that stuff, was the difficulty was making sure that the voltage drop across those components that are variable are the same, and that at the end of the design of the output, that the output current that would be going towards the sensor would be consistent. It would always remain the same across it, and we kept it at a, I believe the current that we used at the end was 4.3 milliamps, which is within the safe range of the sensor. And specifically, in the sensor, there are 2 prongs. I'm not sure if you're able to see that. These 2 prongs. The yellow one is a ground wire, so it's connected to the ground part of the constant current source, and the green one is the positive side. And going up to it, I'm not sure if you can see it directly, but there are a couple prongs that are snipped. Those are the thermistor portions of the sensor. So the sensor is a thermopile and a thermistor. A thermistor is just an array of thermopile sensors. So we originally weren't sure about which one we would use, which one would be more effective when designing the circuit. Do we need to connect it to the thermistor portion? Would that be more accurate, or just the thermopile? When we determined that it was the thermopile portion that would give us the more accurate reading, considering that we're only looking at one measurement at one time.
Okay, thank you.
So I have a question. How did you say this would be used for 2 weeks? That somebody would wear this 24/7 for 2 weeks?
Yeah, that's right.
Yeah. Okay. And they would sleep with it on.
Yeah.
It would be on while they're sleeping.
Yes.
Okay.
So one of the testing validations that we were going to do was like a test for like comfortability almost. And so for that sleeping thing that you mentioned, we were actually gonna, like, after the prototype was assembled, each one of us was gonna kind of wear the device for a day or two and kind of sleep with it, and then see like the issues we were gonna have with it in terms of comfortability, and we can correct for that. But again, we didn't get to do that like actual testing.
Right. Okay, that's good. Yeah, you made a comment about, I think somebody used the term semi-biocompatibility. I would just suggest it's really either biocompatible or it's not, and you want it to be not semi. But wearing it for a day, I think you said you tried that. That's a great, kind of first cut. But if it's only in for 2 weeks, you could actually have somebody as part of your planned comfort test. They could wear it around their ear for 2 weeks, and you could look and see if there's any signs of inflammation or anything like that. There's also standards for biocompatibility tests that you do to check skin sensitization, irritation, stuff like that. That's beyond the scope of this project. But I just wanted to mention that. And then the last thing I want to mention is the prototype you showed us. Now that is not how you envisioned, like back in January, that's not what you thought your final prototype would look like, right? You thought you might have something that somebody could actually wear that would be small. And because I was looking at those big wires and that big thing, you're not going to shove that in somebody's ear. You basically were able to create kind of like a proof of concept prototype, just something that shows you can measure temperature, you could store the data and all that. It's certainly bigger than what it would look like, but I'm assuming that miniaturization didn't occur because of the fact that you did not have the resources you needed to do that.
Yeah, and we weren't completely far off from it. I mean, from this design, this white breadboard portion would be taken off, and I'm trying to go down here, but you can see like the kind of the copper circles. Those are conductive. So underneath this white breadboard, if we were to take it off, there'll be more of those copper conductive rows. So we would just have to connect the device or solder it basically to those, so it wouldn't be as large. And the wiring, the prongs are exposed. So the way we would do this is we would put rubber around these prongs and then use heat to close it off. It's a common practice amongst R2D sensors to heat it that way, and then we would basically do like one of those rope tension techniques. So the ground wire and the positive side wire would intertwine with rubber being obviously the insulator in that, so there wouldn't be any actual open metal touching each other. And then there will also be enough tension, so whenever someone's moving around, they wouldn't have issues of something maybe snapping or pulling off. So we weren't completely far off from where we wanted to be. It's just we didn't have the resources or the face-to-face and medium to medium interaction for the whole design to basically get down to the size that we wanted it to be originally.
Right, and you also, it sounds like you weren't able to actually test your prototype just to see if you got the right signals and everything was able to be, collected and all that. But that's what a future team might be able to do. So, okay,
yeah,
great.
I think.
Yeah. So,
I just wanted to say,
go ahead.
Probably the biggest thing is just making sure we had a safe environment for testing. I could have 100% tested it. It's just, I think the most important part is just making sure there's a safe environment, like in an electronics lab, to fully test it and being electrically isolated from the system.
Yeah, well, that's important. So we don't want anybody starting a fire in their apartment, testing their senior design prototype. So, okay, I see that we're right a little past our half-hour time block. So I think what we'll do is